Students, in the last period, we have solved some examples of metric space. In the today's lecture, we will see some definitions and one theorem also. So, first of all, we will see what do you mean by open and closed sphere. Before that, we must know what is meant by open interval, closed interval, and we have studied in first year and second year also. Open interval means the set of real numbers lies between A and B, that is the open interval. And the set of real numbers lies between A less than or equal to x less than or equal to B, that is said to be the closed interval. So here we are going to see the open sphere. So first of all, we'll see open sphere. So let xd be any metric space and small a belongs to capital X, then for any r greater than 0, the set SR of A, this is the notation, R suffix, SR of A in curly bracket x belongs to capital X such that d of xa is less than r is called an open sphere or open ball of radius r centered at A. So it means if we take an element B belongs to this SR of A, what will happen? Distance of BA less than R. If we take alpha belongs to SR of A, what will happen? Distance of alpha A less than R. So we can verify this. So this is called as the open sphere. Now, the set SR of A, square bracket here we are using, that is the curly bracket x belongs to capital X such that distance of xa less than or equal to r is called closed sphere of radius r centered at A. And obviously all the points which are in open sphere must be are in closed sphere, and therefore we can say that this open sphere SR of A is proper subset of closed sphere SR of A. Now we will see what we mean by diameter of set. Diameter of non-empty subset A of X denoted by D of A and is defined as D of A is equal to supremum of D of AB. AB belongs to capital A. Supremum, you know, in the first year and last year also we have seen the concept of supremum infimum. Now if D of A less than infinity, then the diameter is said to be finite, otherwise it is infinite. Now come to the next point, that is the bounded metric. Bounded metric, you know, bounded set. In second year we have seen that. What do you mean by bounded set? A set A is said to be bounded if there exists k greater than 0 such that mod x is less than or equal to k. Now here we have to define bounded metric. Metric D on a non-empty set is said to be bounded if there exists a real number k greater than 0 such that distance of xy is less than or equal to k. That is d of capital X is less than or equal to k. Then this space xd is called as bounded metric space. We have to see some more theorems, and in that theorem this concept will be useful. Now come to the next point, and that is very important point, that is the neighborhood of a point. Let xd be a metric space and A belongs to capital X, then a subset n a suffix a of capital X is called neighborhood of a point A belongs to capital X if there exists an open sphere SR of A centered at A and contained in NA. That is, in other words, SR of A is a proper subset of NA for some r greater than 0. So this is the neighborhood of point in this metric space. This is very important concept. For example, the set R of real numbers, it is the neighborhood of each of its points. Why? Because if we consider one open interval and if we see every real number lies between that A and B. But on the other hand, the set n of natural numbers is not neighborhood of each of its points. Now why? Suppose we consider one interval, for example 1, 4. So there are so many points lies between 1 and 4, but every point lies in this interval is not natural number, and therefore the set of natural number is not neighborhood of each of its points. Open interval AB is always neighborhood of each of its points. Now we will show one example. Prove that every open sphere is a neighborhood of each of its points. This we are going to show now. So proof, let SR of A be an open sphere and X belongs to SR of A. We are considering one open sphere SR of A and we are taking one point X belongs to SR of A. Now there are two possibilities, either X is equal to A or X is not equal to A. So first suppose that X is equal to A, then what happens? X is equal to A, then A belongs to NA, that is subset of SR of A, and therefore suppose that X is not equal to E. Now in order to prove that SR of A is neighborhood of X, we have to show that there exists R1 greater than 0 such that SR1 of X is subset of this SR of E. Now X belongs to SR of A. What does this imply? Just we have seen the definition of open sphere. So what does this imply? X belongs to SR of A implies D of X is less than R. Now let us take R1 is equal to R minus D of XA. D of XA. Then Y belongs to SR1 of X implies, by using triangle inequality, D of Y less than or equal to D of YX plus D of XA, which is less than R1 plus D of XA, which is equal to R. That is, Y belongs to SR of A implies SR1 of X is subset of SR of A, and therefore every open sphere is neighborhood of each of its points. Now let us see definition of open set. What do you mean by open set? Open set means a subset G of metric space XD is said to be open in X with respect to the metric D if G is neighborhood of each of its points. In other words, if for any A belongs to G, there is an R greater than 0 such that SR of A is proper subset of SR of X. It means if it is neighborhood of each of its points, then that is said to be the open set. For example, open interval, it is open set. The set R of real numbers, it is open set. Why? Because it is neighborhood of each of its points. Now on the other hand, suppose we consider N, set of natural numbers, it is not open set. Why? Because it is not neighborhood of each of its points. Why? We have discussed earlier. That is, if we take an open interval AB, then all elements are not natural numbers, and therefore it is not open set. Here I have mentioned examples. The empty set phi and the entire space X on metric space are also open sets. Empty space, why empty space is open space? Because open set means it is neighborhood of each of its points. But what about phi? There is no element in phi, that is an empty set. Therefore, we cannot say that it is not neighborhood of each of its points. That's why due to this logic, it is open. Now every open sphere is open set, because just we have proved in one example above that the open sphere is neighborhood of each of its points, and therefore naturally it is open set. Now the set R of real numbers is an open set. Now equivalent matrices. Two matrices D and D dash are said to be on the same set X are said to be equivalent if every set open in XD is open in XD dash and vice versa. It means suppose there is one set which is open in XD, then it must be open in XD dash, and then we can say that these two matrices XD and XD dash are equivalent. Now come to one very important theorem. In the statement is, in any matrix space XD, there are two results here. First is the union of an arbitrary family of open sets is open, and second, the intersection of finite number of open sets is open. So let us prove the first result, that is the union of an arbitrary family of open sets is open. So first of all, let curly bracket G alpha, alpha belongs to this visual. This symbol we say it is visual. Be an arbitrary family of open sets in capital X, where this visual is a non-empty index set. Let G is equal to union of G alpha. This alpha belongs to this visual. First suppose that G is equal to phi, because we know that every set either it is empty or non-empty. So we have to suppose in this theorem, first suppose that so G is equal to phi, that is empty. Then clearly G is open. Clearly G is open. So now let us suppose that G is not equal to phi. Not equal to phi means there must be some at least one element. So let X be any element of G. Then G is equal to union of G alpha. Alpha belongs to visual, and therefore there is an alpha 0 belongs to visual such that X belongs to G alpha 0, because we know that. What do you mean by union of two sets? Suppose that one element X and which is in the union of two sets, then X must be at least in one of that sets. So that's why there is an alpha 0 belongs to this visual such that X belongs to this G alpha 0. The set G alpha 0 is open because it is the arbitrary family of open sets. So the set G alpha 0 is open. So what does it imply? It implies that there exists R greater than 0 such that this SR of X is proper subset of G alpha 0. And so SR of X is proper subset of union of G alpha. Alpha belongs to visual, because G alpha 0 is proper subset of union of G alpha. Alpha belongs to visual. Hence G means that is the union of arbitrary family of open sets is open. Now proof for second. So here we have to prove that the intersection of finite number of open sets is open. So we have to consider finite number of open sets. So let G1, G2 up to Gn be any finite number of open sets in X, and let G is equal to intersection of Gi. I belongs to N. So first we suppose that this G is empty as usual, and then obviously or clearly G is open. So we suppose that G is not equal to phi. G is not equal to phi means we have to consider at least one element. So let X belongs to G, that is intersection of Gi. I belongs to N, and we know that if there is one element which is in intersection of two sets, then it must be in both sets, and therefore X belongs to this intersection of Gi, then X belongs to Gi for all I is equal to 1, 2, 3 up to n. It means x belongs to G1, x belongs to G2, x belongs to G3 and so on, x belongs to Gn. Now, since Gi I from 1 to n, that is G1, G2, G3 is open, because we are considering the family of open sets is open. So therefore there exists Ri greater than 0 such that Sri of x is proper subset of Gi for all I is equal to 1, 2, 3 up to n. So how we have written this? As we know that G1 is open, so therefore there is R1 greater than 0 such that SR1 of x is proper subset of G. G2 is open, so there exists R2 greater than 0 such that SR2 of x subset of G. So here in general, for I is equal to 1, 2, 3 up to n, we have written this. There exists Ri greater than 0 such that Sri of x is proper subset of Gi. Now, let R is equal to minimum of R1, R2 up to Rn. So we are considering R as minimum of this. Then R greater than 0, R greater than 0, because R1 greater than 0, R2 greater than 0, Rn greater than 0, and we are considering the minimum of this, and therefore this R must be greater than 0. And we have SR of x is proper subset of SRI of x, that is proper subset of Gi for all I 1, 2, 3 up to n, and which implies that SRI of x is proper subset of intersection of Gi from 1 to n, that is equal to G, and hence G, that is the intersection of a finite number of open sets, is open. So in this way we have seen this theorem. So today I have to mention here all the students, I have given one notice on our group. You have to join our Google Classroom. Otherwise, we will not consider your presentee. And one thing more, you have to give feedback, at least one feedback in one day about the theorem or whatever your difficulties, that we have to mention in that Google Classroom. So note this point. Thank you.